Good morning, Year 13. Hope everything's alright. You'll see that I've sent you an email with this past paper question in it. Now, as we were doing in the lessons, what I wanted to do was go through not so much the answers, but some of the exam prep on this. So straight away, I'm going in and I'm identifying some of the key points. So for example, it says 0.1 moles per decimeter cubed of sodium hydroxide is added to 25 centimeters cubed of a solution of a weak acid HX. Okay, so I'm automatically thinking I've got HX, and if it's a weak acid, we've got that double-based arrow going to H plus plus X minus. Okay, straight away that's in there. Do apologise for unfocusing. It says here then the graph is plotted the pH against the volume of sodium hydroxide, and the first pH started recording after 20 centimeters cubed. And as you can see down the graph, that's where the first point is. Dead simple, dead straightforward. Now, the moment it does that, what we've got to do is work out at what volume the solution cancelled out. Now, this here will mean that I have to work out what the volume is for this point. So I'm going down, and that to me is looking straight away at 24 centimeters cubed. Okay, so that's giving me some of the information. So I know now from this that I took 24 centimeters cubed of 0.1 mole per decimeter cubed sodium hydroxide. So I've got two pieces of information there. Question one is literally just working out what the range is. So I would say that's where the curve stops, and I would say it's near there. So I'd read across those values onto the x-axis, sorry, the y-axis. That would give that. Now, this equation, give an expression for the Ka. Now, I'm going to write down the Ka equation, which, as we know, is dead simple, dead straightforward. If I was going to do Ka, it's H plus times the concentration of A minus, which is conjugate acid and conjugate base, over the total concentration of HA. Now, straight away, I've got those two together. The question's actually asking for HX, so you're going to have to transform that formula into HX instead of HA. That should be quite self-explanatory, to be honest. Right, turn over the paper. Calculate the concentration of HX in the original solution. Now, straight away we're going back to the equation, which is moles equals volume times conc. Now, this volume we know was the 24 centimeters cubed that we worked out for the graph. Focus. This, we know, is the 0.100 moles per decimeter cubed from the answer. From that, you should be able to calculate that question very, very simply. It's just a matter of plugging the numbers in, remembering you've got to convert this to decimeters cubed in order to get the correct answer. Okay, part D says calculate the pH of the solution of HX before the addition of it. Now, what you get from this is you get the answer, which is the number of moles per decimeter cubed of HX. Sorry, apologise for that. And you work from the equation that Ka is equal to, and I know there is an assumption that we're going to have to work this out. I've got Q and D, which is the answer, sorry, Q and C, apologise. Q and C, which is the answer to this question. So this answer would go underneath. Now, assumption that we're going to have to make here is that these two values are identical, so we end up with Ka is equal to H plus squared over H x. Rearrange that equation, and what you'll then be able to work out is the concentration of H plus at equilibrium at the initial point, and then remember that pH is equal to minus log the base 10 of the H plus concentration. So I'm just logging in the steps. I'm not telling you how to do it. I'm not telling you the workings out and all that. I'm not telling you, showing you the workings out. It's just how you step it. Right. For part E, it says calculate the pH of the solution. So calculate the pH of the solution when half of the acid is there. Now, the moment it says this, half the acid is reactive, there is that very, very special case that comes into place, which is where, when half the acid is reacted, we know that the pH is equal to the pKa. Okay, so pH at half neutralisation. So half neutralisation, pH is pK. That will then allow you to work out what the pH of the solution would be at that stage. Now, this next bit is a bit of a toughie. Now, half neutralisation is when we get half the volume in, so if that's 24, half the volume would be 12. So from that, you take your answer from question C, and that will be our first point with zero value. I'm not going to go through this too much because I don't really want to give away too many answers. So I'm going to say about, don't know exactly what it is, at half pH. Okay, we can say it's going to be roughly there. Okay, so when I'm actually plotting this out, what I've got to do is I've got to make sure that this part of the graph is flat, because that's where the buffering occurs. As we know that when we first start adding in the acid, the pH rises quickly, then it flattens out, where it's meeting the buffering point, and then we've got to curve this graph around so that it carefully joins up and joins up. Now, you're going to have to tweak that around with your values, so that your values make sense. That then covers the whole of question 1. Okay, now question 2. Oops, is that? Yeah, I thought question 1. Yeah, question 1. Question 2 is not that question. That's question 2. Okay, dead simple, dead straightforward. You've got the equation at the top, you've got your graph plotted on there. First question actually here is suitable apparatus that you use to measure sodium hydroxide. Now, as it says here, you are adding a range of sodium hydroxide. I would suggest that should be screaming a piece of equipment at you, because we always use Brex to add a range. We use a pipette for an exact volume, a Brex for a range. And it says, use the information of the curve, explain why the end point correction is difficult to judge accurately. Well, looking at this, I'm looking and saying, right, it sort of starts there, and it sort of finishes about there. That's actually quite a reasonable range. So to use an indicator that says, oh, I'm going to go, and actually you can't, it's not easy to look at. So I probably would say that the indicator is not easy to use on that one. Question C. Okay, part C on this. From the pH, There's my special function. Okay, so question part C, that's it. He told what the pH is. He told us 11.8. Use the pH and product of water to calculate the concentration of hydrogen ions at so because we know this, we know that the concentration of hydrogen ions is equal to 10 to the minus pH. So we should be able to work out what the concentration of hydrogen ions are. Now, from that, we've got the equation Kw is equal to H plus OH minus, and it says here concentration of hydroxide ions. You should be able to work that out using that equation because all the values have been given for you. Well, part D, this is where we go back to that acid dissociation constant, and we say that at equilibrium, what we get is the concentration of NH3 is equal to the concentration of H minus ions. So we end up of H plus ions, apologise. So that we end up with this equation being Ka is equal to H plus squared over NH4 plus. And then we can, from that, we should be able to calculate the Ka. So pretty much motoring through this now. Again, we've got our ideas on this pretty much sorted. Part E, a solution containing an equal concentration of ammonia and ammonium ions. Okay, so if you go back to that last question, if it's an equal volume of ammonia to ammonia hydrogen ions, so ammonia to ammonium ions, what we then end up with is the idea that Ka is equal to H plus ions. So from that, we can then work out that Ka, minus log of Ka is minus log of H plus ions. So we should work out the concentration of that one. Right, question 3. Straight away. Ethanedioic acid. Love this. Okay, so it's a diet. It's got 2 acid ends to it. And it says here it's initially acts as if it's monoprotic. In other words, only giving up a hydrogen ion. Now, it says then use the concept of electronegativity to justify why the acid strengths of the ethanedioic acid and ethanoic acid are different. If we're even going to go and do any comparison, what we've got to include is the concept or the idea of what is ethanoic acid. Well, how are these two different? What's going to happen? Well, straight away, if we use this as being the definition of an acid, if we compare the R groups, so ethanoic acid, you've got R is equal to CH3. With the ethanedioic, R is actually equal to COOH. And that means that it actually has quite an impact. This Okay, it's quite electronegative. Contains two electronegative groups, so it's electron withdrawing. This is non-polar, so therefore it tends to be electron pushing. So we have to start thinking about what that effect will have. And that's where the 6 mark comes from, is explaining that in more detail, what effect that part will have on the group. Right, part B, going on to that, part B is quite a challenge actually. It's really worth having to think about. First thing you need to do is identify what the heck is going on with this question. Okay, it says here, you're adding that amount of a substance to that amount of ethandiolic acid. So you're doing a base, you're using a base buffer. So what we need to do is work out the number of moles, and I'm going to put this. So you can work out the number of moles of ethandiolic acid remaining after you've added the sodium hydroxide. Now, the only way you can do that is, that's the amount of ethandiolic acid at the beginning, that's the amount of sodium hydroxide which is going to be taking away some of the H plus ions, so it's going to take away that many H plus ions. So once you've got that, you should be able to work that. It's quite simple. Times 10 times 2. Once you've got that, you then go into the Ka equation. So Ka is equal to H plus A minus buffer. Rearrange the equation, calculate the pH. Okay, that's where we're at the moment. I've got to find the last part of the question paper for you, which is this one. Right, the hardest part for this one is straight away it's asking what the equation is. So in a titration of acidified solution containing ethandiolic acid with 20.2 centimetres cubed with 2 moles per decimetre cube potassium manganate, calculate the balanced equation. Right, this is one where we're going to have to straight away think about what's going on. So essentially what we're going to end up with is H2C2O4. The reason why it's H2 is it's dissociated, so it's lost 2 hydrogens. So I've lost my 2 hydrogens. I'm then reacting that with the manganate ions. Okay, so manganate ions. Now, what happens to that is that is then going to go to MnO, manganate, 2 plus ions, and we're going to end up with this whole mess of what CO2 plus H2O. Now, factoring around with this and you have to balance that as your first step. Okay, there are obviously going to be some H plus ions on this side as well. That's why I said dissociate. So you have to balance all that out. Come on, thank you. You have to balance all that out and then come up with the equation. Once you've got the equation, what that will allow you then to do is to work out the number of moles. So once you've got the equation, you do moles of KMnO4, which is actually that in that equation. That, once you've worked that out, you can work out the moles of H2C2 1.4, and that will then allow you to look at the concentration. I'm hoping that now will give you a bit of a hint on how you work these questions out. I've tried not to give you any of the answers because I want you to have a go at working these out yourself, but I've given you enough thoughts to direct you on where to go. Speak to you all soon.